object, then of course the bear simply keeps moving further and further out. If equal in size, it'll be exactly halfway in between. And that's what we mean by the Taylor tensor of objects that revolve or orbit one another. We're trying to take a chain which is hanging down the side of the building and lift it onto the roof. Now, it takes more work for the bottom portion of the chain because you have to lift it to create resistance than it does for the top portion of the chain. In this particular case, the chain has mass per unit length equal to 2 kilograms per meter. The chain is 20 meters long, so it has a total mass of 20 times 2 or 40 kilograms. Again, it takes less work to fit this portion of the chain to the roof as it does this portion to the chain. So how do we do that? Well, let's review something about work done to lift objects. Let's say we have an object of mass m, we want to lift that to a height h to this location right there. The force to lift it would be equal to the force of gravity, which is the mass times the acceleration of gravity, mg. And when we apply that force over distance h to there, that will then be the work done. Work is force times distance, which in this case is force times the height gained by the object, which is mgh. That's a common equation for work done to lift an object over distance h. But here we have to do it a little bit different because we're lifting different portions of the chain at different distance. That will help us if we use the coordinate axis x as being downward, so the greater x, the more amount of work it will take to lift that portion of the chain up. So what we're going to do is we're going to chop up the chain into small little pieces of length dx. All of them will have a small amount of mass dm, and we're going to lift every piece up from wherever it is to the top of the building, which means that the work done will be equal to, or let's say, let's start with the work done for a small little segment. We'll call it the dw for this little segment right there. That will be equal to, well, let's see here, it'll be equal to the mass, which is dm, times acceleration to the gravity, times the distance x through which we have to lift it. And of course, then to find all of the work, we should have to integrate over moving all the little segments like that. So w will be equal to the integral of dw, which is equal to the integral from x equals 0 to x equals 20 of dm times g times x. Now, our variable in here is x, and our differential is dn. Of course, they have to be the same variable, so somehow we have to convert dm into some units of dx. Alright, so the mass dm is equal to the smaller length dx times the mass per unit length, and for convenience, we call that a constant c. C is 2 kilograms per meter, so we have to multiply it times c. So we can actually replace dm by dx times c. Again, it's the mass per unit length dm. Oh no, the mass per unit length c times the length gives us the mass of the small little segments. So this can then be written as the integral from 0 to 20, and instead of dm, we can write c dx times g times x. And then, of course, we can pull the c and the g out of the integral sign because they're both constants. So this is equal to c times g times the integral from 0 to 20 of x times dx. And that will then be all the work done to pull the entire chain up onto the roof. Let's go ahead and plug in the numbers. Well, first we have to integrate. Let's do that first. This is equal to c times g times x squared over 2, evaluated from 0 to 20. Plug in the lower limit to get 0. Plug in the upper limit. You get, well, the 1/2. I'll put it front times c times g times the quantity 20 squared. So now to calculate the total work done, we plug in what all those are. Work done is equal to 1/2 times c. C here is 2 kilograms per meter, so we'll put down 2. G is 9.8. And 20 squared, which is 400. Of course, that will be in terms of joules. And the 2 cancels out to 1/2. 9.8 times 400. That would be 3, 9, 2, and 0. And so that is the total amount of work done to take this chain and lift it on top of the roof. Now, to show you that since this is a linear relationship, notice that the amount of work done is linearly proportional to the distance away from the top of the roof. What we could have imagined, we could say, well, what if all of that mass of the entire chain, so let's get the total mass, m of the chain, is equal to the length of the chain times the mass per unit length times c, which is 20 meters, times 2 kilograms per meter, which is equal to 40 kilograms. Now, what if that entire mass of that chain had been at the halfway point, 10 meters down? Then the work done would be equal to mgh, which in this case would be the total chain mass of 40 kilograms, times g, which is 9.8 meters per second squared, times the height from the middle point to the roof would be 10 meters. Notice that we didn't get the exact same result. Yes, it would be. So that would give us 400 times that, or 3,920 joules. For a moment there, I thought, wow, I was not sure this is the exact same result. Notice we can simply integrate over every little segment of the chain, or in this case, since the function is linearly dependent on the distance from the roof, or the distance that we have to lift it, we can then say, let's take all of the mass of the chain, put it at the middle point, lift it from there up to there, and we will get the exact same result. And that's how it's done. subgiant because the subgiant does not give off a lot of ultraviolet light and not as much blue light in comparison to the blue giant, of course, which has a big diminishing of the flux density of the light when it's being covered by the red giant over here. So you can see that when you look at the various bands, you can see when the red subgiant is reducing in light intensity and when the blue giant has diminished in light intensity when one star is in front of the other. So you can see that when we analyze the light coming from the two stars in the various wavelengths, you can really get a sense of what we're looking at, and you can then make the connection between the light curve that we see in the binary star system and the way the active star system looks. And it's a nice example to see how nice we can use this light curves to determine the exact definition we're dealing with, and that's how it's done. Methodologies can be used for systems that are completely constrained. Notice that this object here is attached to two blocks, one on each side, and it cannot move at all. Even though we're applying a force at the top, nothing is going to move. But yes, we can imagine that it could move. We can have a virtual displacement and a virtual movement, and therefore we can do virtual work. And we're going to try to find the reactionary force v sub x here because we're applying a force at the top. Now, to try and find v sub x, what we're going to do is we're going to apply the exact same technique that we did with the example. But again, we're going to find here because we do have to take into account that these are vectors, so we're doing the top product. These are vectors theta times the cosine of the angle between the two, since they're both acting downward and between the two is 0, so we take the cosine of 0 degrees, plus v sub x times dx. Now dx will be 2L cosine of theta d theta, 2L cosine of theta d theta times the cosine of the angle between them. Now notice that the x is pointing to the right and dx is pointing to the right, so they're both pointing straight at the cosine. And of course that's equal to 0, and equal to 0. Alright, now notice this is equal to 0. Both terms have an L in it, so L cancels out. Both terms have d theta in it, so that cancels out. So we're left with on the left side, we have f times the sine of theta times 1 plus d sub x times 2 times the cosine of theta times the cosine of 0, which is 1, and that's equal to 0. So now if we move f sine of theta to the right side, so we have d sub x is equal to, okay, put that here for now, so times 2 cosine of theta is equal to minus f times sine of theta. And now when I divide both sides by 2 times the cosine of theta, I get d sub x is equal to minus f over 2 times the sine divided by the cosine, which is the tangent of theta. And this is the force d sub x. Now, it's negative. The reason why it's negative is because d sub x is actually acting in the opposite direction. Now, this lever will try to slide to the left, and the block will hold it in place by pushing it will try to slide to the right, and the force d sub x will act to the left and keep it from going to the right, so therefore d sub x is the negative f over 2 times the tangent of theta, indicating that we are flying here in the opposite direction from the way it actually acts. So that's how we find any forces from any members by using the first force. If we have no movement with the space system, we can still imagine that some part of it can move in a physical sense, and only something towards that, not that small amount of space. And that's how it's Welcome to our lecture line. Now let's take a look at... Welcome to our lecture line. Now let's take a look at eclipsing binaries to see how we can determine the size and mass of these stars involved in the eclipsing. Well, first of all, we can identify the light coming from the various stars, the intensity of the light, when we look at certain bands of light. We have the 1.6 micrometer band, which would be strong for red stars, and relatively weak for blue stars. And I say relatively weak relative to the total intensity. We look at the V band and the V band. The V band has the longer wavelength, so it would be stronger, relatively speaking, again, for the red, orange, or yellow stars. The V band is relatively stronger. The intensity of that band, we can then expect it to be a much hotter star, like a white or a blue star. Coupled with using the 7-Boltzmann law, where the amount of light per unit time or energy per unit time received from a star is equal to the emissivity constant, the Boltzmann constant, the area surface area of the star, and the temperature to the fourth power, and coupled with Wien's law that relates the highest intensity of wavelength that we receive from a star to the temperature, we can then use that and the color luminosity relationship of the HR diagram to try and determine the kind of stars that we're dealing with. Obviously, when we have the color of the star determined by using certain filters, we can then pretty well approximate using the HR diagram what type of star and what size star we're looking at. Another way which we can determine the size of the star is to realize how much the light is being dimmed. Now notice, when the small star is behind the large star, we have a dimming of that light, and so we can then determine how much light reduction is there because the small star is no longer being seen. Here, this is the reduction when the small star is in front of the large star, and lots more light is being held back. But then if we add the reduction of the small star to this, we can then see this would be the total reduction if no light were received from the small star that's in front of the large star. And so based upon that, we can also determine what size star we're dealing with. Another thing that we can do is figure out, once we know the orbital radius, and we know the period is of course easy to calculate, but if we could somehow measure the orbital radius, then we can determine how fast the star moves, the small star moves around the large star. We can find the tangential velocity of its orbit, and then we can determine the diameter of the small star by measuring how long it takes for the star to disappear completely behind the large star, or for the star to disappear in sense completely in front of the large star, either way. So we can see how long that takes, and so we multiply that time times the velocity to get the diameter of the small star, or the amount of time that it spends behind or in front of the large star. We can then determine the diameter of the large star by multiplying the tangential velocity of the small one times the time that it spends hidden by the large star. So those are some of the techniques that we use to try and determine the mass and the size of the stars in eclipsing binaries. Of course, you're going to want to see some examples of how we exactly do that to get more of a feel for it. But at least at this point, you have some good ideas of the different types of techniques we use to come up with the size, the mass, and the size of the various stars in eclipsing binaries. And that's how it's done. Welcome to our lecture online. Here we have a system that is partially constrained. On the left side of the system is attached to a block. You can swivel this way, but you cannot move either up or down, left or right. This member here is attached to this member. This member can actually move to the right and push this block to the right, so therefore there is a force pushing to the left. I have a force trying to drive the members down. I have a force here to the left. We have two reactionary forces. We have one at A and one at B. Of course, at A we have both one in the X direction and the Y direction. The one at B we only have one in the Y direction only. So this would be D sub Y, if you want to call that. Okay, but since D sub Y is pointing perpendicular to the change in the direction, the X here, that means the angle between the two is 90 degrees, so that would simply ignore D sub Y, and we can ignore A sub Y and A sub X because this point right here does not move at all. So there's no virtual work done. So what we're going to do first is we're going to define the initial distance from here to where the force is acting initially. We're then going to define the change in the distance dy. We're also going to define the distance x from here to here, and then the distance dx. So based upon the angle relative to the vertical, if we assume that this is going to be the same on both sides, we can say that y here is equal to the length of this member times the cosine of this angle because it's adjacent to the angle. So we can define y sub naught as being equal to the length of the member times the cosine of the angle theta. We can also define x here. Well, that would be L times the, well, if we put the x over here, that would be opposite the angle, so this would be L times the sine of theta, but we have to multiply times 2 because there's two members there. So that means that x sub naught is equal to twice the length of each member times the sine of the angle theta. Now we can find the change in y and the change in x in terms of the change in the angle theta. Just going to circle down through a small angle d theta, which means that dy d theta can be found by taking the derivative of this. That would be, well, the derivative goes out as a negative sign, so minus L times the sine of theta, and then we bring this d theta over here. We can simply write that dy is equal to minus L sine theta d theta if we take the differential of the angle. We can do the same with the change in x. The x can be defined as being the derivative of this, which would be 2L times the cosine of theta d theta. So now we have